Alright, science friends, we're back for Unit 2. This is the very first video in Unit 2. That's why it's given Unit 2 A.1, so the very first video. This unit is going to focus a lot on the forces within a molecule as well as the forces between molecules, intra versus intermolecular forces. So we're just going to get started. Our first video is just going to be about basic, how we know there are interactions between particles. How do we know that particles interact with each other? So I'm going to jump off screen, copy these notes down, I'll jump back on, and then we'll talk about it. All right. Alright, hopefully that was enough time for you to copy down the notes. Intermolecular forces, or IMF as it's more commonly referred to, because intermolecular forces is a mouthful. Intermolecular forces are the attractive forces between two particles. So it's not within a particle, it's not bonds, but it's in between two particles. They're kind of like very weak-ish transitive bonds that kind of stay, kind of go. Another way you can think about it is how sticky the particles are. If they stick together, they have high intermolecular forces. If they don't, then they have lower intermolecular forces or no intermolecular forces. So IMF is how sticky a compound is. The states of matter are a result of intermolecular forces. So compounds that are solids because the IMFs hold them together. So a solid is a solid because the intermolecular forces hold them together. So butter is a solid because the intermolecular forces within butter atoms. I know it's an oversimplification, there's not a butter molecule, but the intermolecular forces between butter molecules hold them together. As a result, they're stuck in place, they can't move past each other. That's why solids have a definite shape. All right? These molecules are so sticky that they're kind of stuck together and they can't move past each other. And then they have high IMFs. So solids have high IMFs. So if it's a solid, it has high IMFs. If it has high IMFs, it's a solid. So that's kind of how we know the difference between those two. All right, let me grab my eraser. All right, here we go. And let's talk about liquids. Let's talk about liquids. We'll do a different color because that's fun. All right, now, if solids have high IMFs, liquids are going to have like a medium IMF. So not really high, not really low, but kind of in between. That's because the particles can slide past each other. Past each other. So the particles have a little bit more movement. They can't quite yet fly away, but they can slide past each other. It's important to realize that if there were no IMFs, if there were no sticky forces between particles, the particles would just kind of fly away from each other. They would fill the container. They'd be a gas. So liquids have some IMFs. They're stuck together, but not so much that they can't slide past each other. However, they're still close together. I'm even going to put a really close together. So they're still really close together. They're not quite like a gas, which can really spread out, and there's a lot of distance in between, but they're still really close together. And they have a moderate amount of IMF. They have moderate intermolecular forces. So they do have some. It's not a ton, but they do have some. Gases we are going to talk about in the next section because gases are kind of a beast all on their own. Gases are particles that either have so little IMF or are so energized that the IMFs don't come into play, that they just fly apart. They do their own thing. They're able to expand outward. So gases kind of behave on their own, and they have some very special properties that liquids and solids don't have. And so we're going to talk about those in the next couple of videos. However, so we're talking about IMF. It'd be nice if there was some way we could figure out more of a ranking than just high, moderate, low. So there are three things. Viscosity, or viscosity is technically defined as resistance to flow, so how much it resists flowing. We're going to call viscosity thickness. All right. Maple syrup is viscous. It's thick. It doesn't flow. Water is not. It's thinner. It does flow. So viscosity, surface tension. All right. Surface tension is how easily things can kind of pierce the surface. So like, for example, water has very high surface tension. And that's how some bugs are able to skate on the top of water. Or you can have it mound up. If you like fill a glass really, really high, the surface of the water can kind of mound up. How much it beads up on a surface is kind of surface tension. Or how much those molecules stick together and don't want to flow out. And then if we're talking about solids, one of them could be hardness. These three properties help us rank intermolecular forces. So if I have a whole bunch of liquids, I could look at the viscosity and the surface tension of those liquids and rank them from high intermolecular forces down to lower within that liquid range. So it's just a way to kind of tease out the intermolecular forces a little bit better. Last but not least, we are going to, let me just show you a simple little heating curve. This is temp, this is energy. This is solid, this is a liquid, this is a gas. So what happens here is, as you heat up a substance, when it hits a phase change, so this right here would be like a melting or freezing. When I hit a phase change, the temperature stops. However, there's still an input of energy. I'm still adding energy, but the temperature flatlines. It doesn't increase. And that's because it's undergoing its phase change. So for example, ice melting. If I were to put ice cubes in a glass of water, as those ice cubes melt, they keep the glass cold, right? If I drink a glass of ice water now, or if I leave it on my desk for 5 or 10 minutes and I drink it then, it's going to be the same temperature. It's still going to be about 0 degrees Celsius. However, heat's been pouring into it from the glass, from the air around it. So I'm adding energy, but my temperature is not going up. Right? That ice water is going to be ice water until all the ice is gone. And it's going to be the same temperature as long as there's ice in there. But that energy has to be going in somewhere, and it's going into the ice. What it's actually doing is that energy is breaking the intermolecular bonds. That energy is exciting those molecules enough that they're able to start sliding past each other. So even though I'm adding energy, it's not that nothing is happening. It's that the temperature isn't going up because all that energy is being devoted into breaking the intermolecular bonds or exciting the molecules so much that they're able to start breaking those bonds. They're supposed to be able to move past. And by intermolecular bonds, I mean things like hydrogen bonding, London dispersion forces, things that we'll get into later. Alrighty, well that's it for video 1. I hope you enjoyed yourself. Video 2 will be gas loss. Exciting. Alright, bye.